Assalamu alaikum everyone. I hope you're doing well. So in this video we will go over the chapter for IPv6. We've discussed IPv4 so far. We've done questions, subnetting, VLSM, custom subnet mask, all of that using IPv4. Now we will look at IPv6. Why do we need it? And what is so great about it? Okay. So now the problem with IPv4 is that it only has about 4.3 billion addresses available. Okay, and as you might know, that there are around 7.8, if I'm not wrong, 7.8 billion people on this planet. So if all of these 7.8 billion people decided to join, the networks, and, they want to be online like everybody else, then we would eventually run out of IP addresses, because IPv4 only provides 4.3 billion addresses. So that was a very big limitation, let's say, to IPv4, and that is why IPv6 was introduced. There are other versions of IP addresses as well. There's IPv5, IPv2, all of those are there, but IPv4 was the one that was very popular, and I think around 80% of the networks are based on IPv4. But now we're eventually moving to IPv6 because of the same limitation, that we anticipate that more people would join. The networks would want to be online. And 7.8 billion, if all 7.8 billion people eventually join us online, we don't have many addresses available for them then. Okay, so this is just a chart that shows the IPv4 address allocation back in 1933, which is quite a while. I was not born then. So if you take a look at it, the grayed out here, let me use the laser. The grayed out portions here, all of these are the ones that were available back then. So these addresses were available, they weren't taken, they weren't being used. And we also know that in IPv4, not all of the addresses were available for use. If you remember Class D and Class E, the addresses in those classes were reserved for multicasting and research and development, right? So those, again, we cannot use them. So those were reserved. They were unavailable basically. And similarly, the network 0, the network 127, those are also, let's say, unavailable, because the network with 0 basically is the default route, and the network with 127 is basically 127 here. 127 is basically used for loopback or for testing. Moving on, in 2009, we can see almost, I would say almost 95% of the available addresses were then allocated. So we only had a few remaining back in 2009. And if we're like 12 years ahead now, I think we would eventually would be out of those addresses as well, because of COVID, everybody had to move online. Even the people who weren't online, had to move online because of work, because of education, or whatever that was. So yeah, I think that makes it very clear why the need of IPv6 was huge. Now, again, the same thing. This, I think, is it wouldn't be a lot It would be like second nature to you right now, because we see this happening every day. We see that internet is growing. We see that people who don't have like on TikTok, for example, I've seen people who probably live in very, very rural areas making videos. So, you can see how much internet has grown. And this was back in 2005, where Cisco estimated 973 million users. I'm for sure, I for sure know this, that this number would have been surpassed by now. But again, we know that internet is growing. We know that people everywhere are slowly joining, the network, which means the number of devices are increasing. For now, I think everybody knows that in your house or in your family, you would see there are people who carry more than one phone. So that means there are two addresses right there, right? And then we have laptops, we have computers, we have tablets. Now we have IoT devices that also require IP addresses for them to function, right? So that we know that all of that is leading to an increase in the demand for addresses, or increase in the demand of connectivity. Okay, so again, that's what I just said. Everything is slowly increasing, whether that's devices, whether that's the need to connect. It's increasing, and to address that need, we need more IPv6. We need more IP addresses, and that's why IPv6 comes in handy. So, but what is so fabulous about IPv6 that we have to say goodbye to IPv4? That's because we have more space in IPv6 addresses. So in IPv4 address, if you remember, we had 4 octets, and each of those octets had 8 bits, right? So that made it 23 bits. Now in IPv6, we have 16 octets. It is 16 octets, but it's not written in 16, like you don't write 16 octets. What we use when we write IPv6 addresses is called hextet, and it's nothing but 16 bits. Okay, and so you have basically 8 hextets, which each of them have 16 bits. And if you calculate 8 into 16, you would get 128 bits. Now, like I said, with IPv4, you almost have 4.3 billion addresses. And with IPv6, you have 340 undecillion IP addresses. I do not even want to read this number out, but these are the number of addresses you would have with IPv6, and that's why we want to move to We would want to move to IPv6, because now we have a lot more space to basically have more devices or people joining networks. Okay. Now, how are they different? How is IPv4 different from IPv6? Now, if you remember, IPv4 addresses were written like this. You would have a number here. So, for example, it would look something like this: 192.168.27. Let's say 10. Okay. Now, each of these were considered octets. I mean, they're decimal converted numbers, but they represent octets usually. And then these octets are separated with periods, 3 periods or dots. But when we come to IPv6, we have 8 hextet, like I said before, and each of those 8 hextets has 16 bits. And each of these hextets are basically separated using colons. So you have 7 colons, 1, 2, 3, 4, 5, 6, 7. And the remaining are basically just the numbers, the converted numbers. Okay. Now these, in IPv4, you had decimal format. So you would convert from binary, you would get a decimal number, right? Between usually 0 to 255. That was our range. We couldn't have 256, right? Here in what's it called? IPv6, what we have is we have groups of 4 hexadecimal digits, case sensitive from A to F. What does this mean in normal English? It just means you will have numbers from, let's say, where is the cursor? Yeah. So you will have numbers from 0 to 9, okay, and A to F. Those are the possible numbers you can have. And you will see how to write all of that. Don't worry about it. Now, here in IPv4, you do not have leading zeros. So if the IP address was something like this, like the one that I just showed you here, you cannot write it this way. You can't write it as 192.168.027.010. You can't write the leading zeros if one of the digits is missing. We omit that, right? But in here, in IPv6, it is optional to write the leading zero. So your IP can have a 0. The numbers in the IP address can have 0 in the beginning. So it could look something like this: 0, 1, 0, 0. There's some number here, and then there is some number here. So it could look something like this. Again, I forgot to, I think, mention this, but with each of the hextets, you only have 4 digits. Okay, so one hextet will have 4 digits, and then you have a colon, and then the next hextet also has 4 digits. But here it was different, right? Here you could have only 3 digits. You can't go more than that. So, okay, so that is about the leading zeros. Then the successive zeros must be included. So here, if I take the same IP address that I took in the question, okay, 192.168.027.010. So this 0 cannot be omitted, because if you remove this, then the whole address changes. Sorry, it shouldn't be written as 0. So if it was 10, you can't remove the 0, because then the whole network address or the IPv4 address will change. Now, successive zeros can be represented with double colon, and this is something with double colon, and this is something we will look at once we take a look at the rules, but just keep that in mind for now. And here we have the rules. So basically, like I said, your IPv6 address has 8 hextets. These are your hextets. So this is 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, if you see here, you have all zeros. So instead of writing 0 4 times, you can just, like we saw before, you can just remove the leading zeros. These are considered as leading zeros. So you just remove the leading 0 and just leave the last one. Okay, that's another way of representing this. Similarly, here you have 3 leading zeros. You can remove those and just write the last 0 here as well. Just remove the 3 leading zeros, write the last 0. Here also there's a leading 0. You can remove that as well. This I think is wrong. Here it should be 130. Okay. But anyway, the leading zeros, you can remove them, how many ever they are, 1, 2, 3, how many ever they are. And instead of that, you just write the remaining numbers. So here, there is no remaining numbers, but there's just 1 0. The 1 0 at the end, you just write it. You can't remove that 0, okay? There's one way of removing that, but I'll show you that later. So that's one way. So again, keeping the same example in mind, we don't have any leading zeros here, so this number remains the same. We have leading zeros here, so we will remove the first 3. Okay. Again, leading zeros, we remove the first 3. No leading zeros, so this stays the same. Then again, you can't remove the successive zero. So these zeros, you can't remove them. You have to write them as it is. So this remains the same. Again, leading zeros, you can remove them. Leading zeros, remove them. And then leading zeros again, remove them. Okay, so now the address becomes a little bit short. Here you see all of them are zeros. So you can just remove all the leading zeros. That's your first rule. Any leading zeros, you can remove them. Okay? So that's rule number 1. Now I would want you to pause the video right now. What I want you to do now is that go to Moodle, and in week 5 you will find IPv6 workbook, the same kind of workbook that we had for IPv4, but it's for IPv6 now, and complete pages 4 and 5. It's based on the rule that I just showed you. Just complete that and come back and then watch the video so that you don't get confused. Okay? So now moving on. So now for the second rule, what we have here is that if you have continuous zeros in the IPv6 address, which means if you take a look at this address, this hex text basically represents .0000, and then this one represents colon, not dot, colon 0000 colon 0000 for this one. So we had leading zeros. From rule 1, we know we can remove those. So you remove all the leading zeros, and then you're left with just 1 0. And it's like this. And in this case, it's continuous, right? So what you could do is remove all of these continuous zeros and just put 2 colons instead. And then the system or the device will figure out that these are zeros. Okay, how many hextets are missing? It will first figure out how many hextets are missing, and then it will replace them with zeros. So this is how it would look. I'm sure this is not very clear, but there are 2 colons here, and those represent the continuous zeros. Now, taking a look at an IP address that is like this one, you have all of these as continuous zeros. So what you could do is you could just write the ones that are not zero first. So FF01, 2 colons for representing that there are continuous zeros, and then 1 0 1, like this. Okay, now you have, for the next one, we have these many continuous zeros, so you would just write it like this: colon, colon, and then 1. Okay, and then all of them are 0, nothing, no addresses there, so in that case you just write double colon. Okay, so that is the rule 2. The rule 1, the first rule basically was if you have leading zeros, you can remove those. And rule 2 was that if you have continuous zeros, you can remove those and just put double colon instead. Okay, so the trick here for rule 2 is that the double colon that we use can only appear once. Okay, you can't have the double colon twice. For example, this will be invalid, because when you put double colon, the system tries to figure out, okay, how many hextets are missing. Okay, and then when it finds out how many are missing, it just fills all of them with zeros. But you if but if you have two double colons, then the system wouldn't be able to figure out how many were missing from each of the double colons. So, for example, it wouldn't know how many hextets are missing here or how many are missing here. It wouldn't know. Okay, so that would mean that all of these three can be the possibilities of IP addresses. You wouldn't have a unique IP address in that case, or you wouldn't know what is the correct IP address, because it can mean that the first double colon might be missing two hextets and the next one is also missing two hextets. The first one could miss three hextets and then the last one could miss one of them. And then this one could mean that there is only one hextet that's missing at this position and the remaining are three. And more variations can happen, but just remember that the double colon can only appear once in IPv6 address. Okay? Now, I want you to pause the video and just complete the exercises that are on from page 6 to 10. Okay? And then once you're done, come back and watch this video. So, how do we represent IPv6? Okay? If you remember from IPv4, we used to have the address itself. Okay? And then we had the subnet mask, or we could even use the CIDR or the prefix to represent the subnet mask. Okay, but in IPv6, the prefix is always there. Okay, here in IPv4, you can either write the subnet mask or write the prefix. It's not mandatory, or it's not required that one of them should. It should be one of, like, it's not required or it's not mandatory that you should only follow prefix or only follow subnet mask. It's up to you. But in IPv6, we always write it with the prefix, okay? And you don't need to write the subnet mask for it, okay? Now here, if you use the IP address in URL, if you use the IPv6 address in URL, you have to put brackets at the start and at the end, okay? And we don't usually write IP addresses in URLs. If you remember, we have DNS for that, right? So, but there are cases where you would want to write an IP address, and that is usually when you're testing or when you're creating softwares. Usually developers, they use local addresses to basically test their work. So you would use it in those cases, but in reality, you wouldn't really write any IP addresses because it would be cumbersome. And why would you then need DNS if everybody was writing IP addresses, right? Now, if you remember from IPv4, I keep getting confused, but if you remember from IPv4, we had three kinds of addresses: network, broadcast, and then host. Okay, here in IPv6, we have something called unicast addresses. These are essentially unique addresses. We have multicast and anycast. Okay, if you remember, in IPv4 we had broadcast addresses, but in IPv6 that is basically discarded. We don't have broadcast addresses in IPv6. Okay, and there is another way of fulfilling that requirement that broadcast addresses were doing, using the all nodes multicast. But essentially, you need to remember the three types, basically unicast, multicast, and anycast. Within unicast, we have global unicast address, linked local unicast, and unique local unicast. We'll look at all of them one by one. So unicast address is an address that identifies a single device. So basically, just like the address that you give to a host, that is the unicast address. Now, within the unicast address, if you remember, we have something called global unicast, right? Now, global unicast means that it is a unicast address, which means it is for a device, to identify a device that is globally unique. Okay, so in the whole world, nobody else will have the same address. Okay, it is to identify the global unicast address is to identify individual device, and it is unique. Nobody else can have it. How can we make a device on a network globally identifiable? Um, and here we're specifically talking about IPv6 addresses. How can we make devices globally identifiable using IPv6 addressing? Okay, so if you remember, we said that IPv6 has 128 bits. Okay, out of those 128 bits, 64 bits are used for network and 64 bits are used for host. If you remember from IPv4, we had different classes, right? A, B, C, D, E. All of these classes had, all the addresses in these classes had network and host portion, but they were different. So for class A, you had only 8 bits, which is 1 octet for the network. And for the host, there were 16 bits. No, not 16. Wait, there were 24, sorry. There were 24 bits for the host part, which is 3 octets. And they were different as we moved down the classes. But in IPv6, we have 64 bits dedicated for the network and 64 bits dedicated for the host. Now, the 64 bits that are used for the hosts, it is actually called the interface ID. Okay, it's called the interface ID. Now, the interface ID basically the interface ID contains the 48-bit MAC address. So every network interface card, NIC, has MAC address. So there is a MAC address for each device, and we know that it is unique. Every device has a unique MAC address. So the the interface ID for IPv6 contains the MAC address, which takes up 48 bits. Now the remaining 16 bits are basically for the addressing. So an identifier derived from the EUI64 address. Okay, now these have 16 bits. Now the network portion, what does it have? We spoke about the interface ID. We said it has an identifier and a 48-bit MAC address for the device, right? What does the network portion have? The network portion has subnets. So basically, it consists of the different subnets that we want. And the remaining portion has the hierarchy, which we will talk about in a minute. Okay, so subnets and hierarchy. So this is what happens. You have 64-bit for the interface ID. It contains EUI address, and then it has the 48-bit MAC address. Okay, here the network portion has the subnet ID that we just spoke about, and then there is also something called the global routing prefix. This comes from your ISP provider. Okay, so you have 16 bits that are dedicated for subnets, and then you have 48 bits that are dedicated for the global routing prefix, which comes from the ISP. So basically what's happening is that this part provides the location of the device. Where is this device connecting from? Is it from Asia? Is it from, basically which country, all of that. The subnet is basically which let's say within Polytechnic, we have different departments. So which department is it from? And then basically the interface ID will identify the host. This is for identifying host. This is for identifying subnet, which department, etc. And then this one is to define or identify the location. Okay. Now, what do we have left? So, what is the global routing prefix? Okay. We have ICANN, which is an organization that handles addresses and names and all of that. So basically they have access and power to everything. Then comes the RIR, which is Region Internet Registry. Okay. Then there is LIR ISP site subnet device. I'll start with explaining these two first, and then we'll move to the next. Okay. Now, ICANN is the short form or abbreviation for Internet Corporation for Assigned Names and Numbers. So they manage DNS root zones, or basically linking addresses with names. So www.google.com, what is the address that is linked to that particular name, things like that. And then coordinates the global IP and AS number space and assigns them to RIR. So they basically handle the addresses that are available. You can't just go and pick one address from the available addresses by your own, on your own. You have to go through these different hierarchies to basically get IP addresses. Okay. So ICANN is at the top, and they basically handle all the names and the numbers that come with IP addressing. Okay. Now, the next one is Regional Internet Registry. I think I said region, but it's actually regional. So Regional Internet Registry. It oversees allocation and registration of internet number resources within a particular region of the world. So basically, the whole world is divided into separate regions. Okay. I'm just drawing them randomly here. I think there are only 5, so I should not have drawn this. So each of those regions basically control which IP addresses are allocated or what registrations take place, okay, over the internet, whether that's for IP addressing or whether that's for domain names. Okay, so if we take a look at it, there are different regions. There are 1, 2, 3, 4, 5 regions, and we basically belong here because we would be in the Middle East, right? And it's controlled by, I think, Europe, or it's run by Europe. So this basic RIR is run by Europe, or is managed by Europe. That would be the better way of saying that. So ICANN has all the numbers available. RIR basically manages the allocation. So you have a pool of numbers available in every RIR, and these are managed. Okay, which address is where? Which pool of addresses are assigned or allocated to which country, etc. Okay. So the next one is LIR, which is Local Internet Registry. It is usually large internet service providers received an IP address allocation from, okay. It is usually large internet service providers, but they could be I can't speak today. They could be regulatory authorities as well. So in Bahrain, we have TRA, which is telecommunication, I think. Telecommunication Regulatory Authority. These, again, what they do is they receive allocations, or they receive IP addresses from the RIR, okay, and they manage these IP addressing allocation within the local region. So for Bahrain, it is basically handled by TRA. Okay. Then we have our ISPs, which are in Bahrain. We have the biggest one is Betelco, then there is Zain, there is STC. Okay, so these ISP or internet service providers, they have been allocated IP addresses from the LIR, which they can then use for their customers. Okay, so these ISPs then provide these addresses to the customers. That's how we have it. So if you have a connection from Betelco, Zain, STC, they give you those IP addresses from the pool of IP addresses that they have. Okay, so if in cases when the customers are organizations, then you have different sites as well. So for example, UOB has one campus in Sakhir and then another campus in, let's say, Issa Town. Okay, and each of them will have different departments. So they need subnets for these departments, and each of those departments have different devices. So they need, addressing for that. So this is where we have our VLSM. This is where we learned how to do VLSM, right? So basically, ICANN has all access to the numbers that are available in addressing. Each region has been provided some numbers. Okay, those numbers are further allocated to local internet registries, and they manage who gets allocated what number. The ISPs get their numbers from LIR, so Betelco, Zain, STC, all of them, they request IP addresses from the local internet registry, and then they give those IP addresses or assign those IP addresses to different customers or organizations, and so on and so forth. And that's how you basically are able to connect. Okay. And this is basically how we also figure out where an IP address is coming from. If you have ever been to those websites where you can put an IP address and figure out where it is from, this is how you know, because there are ranges of addresses that are assigned to different regions. So again, this is what I just said, the end customer of an ISP. So basically, we are customers of ISPs, or organizations are also customers for ISP. So they would then provide IP addresses to them, and then further subnetting would happen based on the requirement of the ICANN assigns the 23/23 prefixes or addresses with the prefix /23 to the LIRs. Okay, and then the LIRs and the ISPs then allocate longer prefixes to their customers. So then they basically subnet it, and they have more addresses that they can then provide to their customers. Okay, and the majority, the prefixes assigned are /48. So these are assigned by the LIR and the ISPs. These, I don't know if they will make a lot of sense to you right now, but I'm sure that it will make sense in the future. But these are just the different types of addresses and how they look like. So if you remember, previously I said from IPv4 that if you are in class A, then usually the first bit is 0. If you're in class B, the first bit would be 1 and 0, and so on and so forth, right? So, but in this case, these are similar, but in this case, you will see that if you have a loopback address, it would look something like this. Everything would be 0, and then you would just have 1 at the end. And if you represent it using the rules that we learned, it would look something like this. So this will be used for loopback, and loopback is nothing but for testing, right? Then you have an address that is for multicast. It would look something like this. Usually all the addresses would have this at the beginning, that the addresses that are used for multicast. The ones that are used for link local unicast are always like this. Okay, and they have they always look like this, like they always start like this. Okay, and then you have global unicast always starting with a 2 or a 3, and then everything else is basically reserved for the future use. Okay, I don't think you need to know this right now, but it will start making sense. Just remember, for loopback, this is the address that you have. For multicast, it would start with FF00. If you see an address with FF00 that is used for multicast, you would know it is used for multicast. And then for link local unicast, you would know that it starts from FE80, so on and so forth. Again, this is for your information, but it will, of course, start making sense once we do more questions about this. So these are just examples of multicast addresses, and multicast is an address that allows you to send packets to multiple devices. Okay, so if you wanted to send packets or data to all devices, you would use this address. Okay, this is for all nodes. If you want to send to all routers, it would be this address. If you want to send to all OSPF version 3 routers, if it doesn't make sense at this point, what is OSPF? Don't worry, you will know it later. But you would use this address. If it's for mobile agents, it's this. If it's for DHCP servers, it's this. So you don't need to. It is good to know these, just like how you would know, the different classes for the IPv4 version. It might come in the Moodle quiz, so it is good to kind of remember this. I would recommend remembering this, but you don't need to know what they are right now, but it would be good if you can start remembering. Okay, so FF022 is for all routers, and this is multicast address. That is why every address is basically starting from FF02. If you see back, for multicast address, we had FF00, right? The only thing that changes is the number after the double colon, right? So that is an example of all multicast addresses. That is it for today. If you have any questions, let me know. I would advise that you do all the workbook questions that are there in this in these slides. And if you have any questions, you can let me know. But this is just kind of an introduction to IPv6. More detail will be provided about this by Mr. Mahmoud. So, yeah, just that. I hope it made sense. If any of it doesn't make sense, please let me know. I was not very well. That was the reason I had to record it. And yeah, I hope you have a good day. I will see you all next time. And thank you for watching.